Oh, good afternoon. I have a new class list. Contrary to appearances, the enrollment is getting larger and larger. Husam Anjum, Abigail Arsenal. Oh, thank you. Alexander Bullen, Jinquan Kao, Jack Ferroni, Guan Yue Chen, Yuja Cheng, Carissa Cho Lee, thank you. Arkaprava Chaudhuri, Siddharth Dagar, thank you. Daniel Dima, Emil Fredfeld, Justin Huth, thank you. Sebek Germania, Germain, Charles Griffin, Henry Grover, thank you. Henry Hu, thank you. Xiao Hua Wang, thank you. Stella Casa, oh, thank you. Alexander Cole, Zhao Shang Lin, Juan Loke, thank you. Yifei Lu, Luke McCutcheon, thank you. Abubakar Mohidi, thank you. Ruben Navasarjan, Jonathan Ing, Rishib Prasad, Syed Mohammed Raza, thank you. You know, at the back of the room, you can hear because apparently there are some speakers there. But I wonder if you can see, and I certainly wonder if I can see. How are you on Qi? Current side. Ewan Wang. Thank you. Hongbo Wang. Dong Wei. Become Wang. Thank you. And second graduate student, Fuyan Gujari. Chen Ye Zhou. Well, I don't see Chen Yi. I don't see Chen Yi online. Oh yeah, Puyan Gujari is online. Well, you're online. Oh, okay, good. Right, okay, yeah, thank you. All right, but I don't see Chen Yi Zhou online. He's in Ottawa. And then Dailin Lee. Haven't met him, but he's registered. No. Yeah. All right. Well, can I ask you what your name is? I'm sorry, I have a. Yes. Hello. It's an urgent call. Yes. 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 I would just like. I can confirm the appointment. Oh, it's canceled. Oh, all right, well, I didn't get that. All right, so it's canceled. Is there a new date? Anyway, I see. And 10/15, March. Oh, 10/50, March 20, March 25th, 26th. Yeah. All right. All right. Well, all right. Thank you. Yes, thank you. Thank you very much. You know, I'll never be able to get in touch with that office directly. Thank you for patience. All right. Well, how many people have you can look up um, uh, Paul Helmos wrote a number of books, including one of them being I Want to Be a Mathematician, and he's considered to be one of the best expositors of mathematics. But he's also a leading figure in the theory of learning operators in Hilbert space. And I've quoted from him from time to time. One of his books is, well, Introduction to Hilbert space theory. One of them is measure theory, what's called measure theory. One of them is called naive set theory, which is can be worth looking at because it's just the opposite of something like Whitehead and Russell, which you might never you might have some difficulty with. And another of his books might have been naive category theory. Okay, and I've forgotten if this book I just mentioned covers category theory, but it's different from set theory. For instance, there's no well, your categories could be sets, okay, but they don't have to be. And it's important to be able to work with the elementary concepts of category theory, because it's just very helpful, very helpful. So what's the category? Well, what's the category of sets? You just look at sets, and then a category has objects that has arrows, and the arrows go between the objects, and you can compose them, and it's a social, and that's a category. Well, you have every object has an identity map, which is an arrow which is you can compose it with itself, and you get the same map back again, and you compose it with so if you have a map between 2 points, an identity map on the main side, the arrow is and then you compose it with this. It can be composed with this arrow. The arrows can be composed with if the head of one, the tail of one begins at the head of the same object where the head of the other one begins. Okay, but that's the category. It's arrows with some the domain, the source and the range, or okay, well, the domain or the codomain, and the identity map on range side is the you compose it with the arrow, an arrow going to this point, then you get the same thing. That's the category. And if you have 3 arrows, and any the first 2 can be composed, and the last 2 can be composed. Then the composition of the first 2 can be composed with the last one, and the composition of the last 2 can be composed with the first one, and you get the same answer. That's associativity. Okay, so it's an example is the category of sets, where the objects are sets, and the arrows are just set maps. And well, in this electronic age, I'm going to have to start bringing chalk. Well, I did bring some chalk, a piece of chalk, my emergency chalk. Don't know if it's actually things will come down to an emergency yet. Okay, so and there's the category of vector spaces, and there's the category of cardinal numbers. Natural numbers are more generally cardinal numbers, and you have two cardinal numbers, n prime. So what is an arrow going between them? There's always an arrow going in at least one direction, okay? And the arrow just says n is less than or equal to n prime, okay? And so that makes the natural numbers a category. And so if you have arrows in both directions, that means each one is less than or equal to the other, and by the depending on how you define cardinal numbers, that implies that either by definition or it implies by the Cantor-Bernstein theorem that they're equal. And that's equals is isomorphism in the category. So what is isomorphism in the category? Well, you have maps. You do have maps going in both directions between 2 arrows. If going forwards and backwards with those arrows gives you the identity map on the first object, and going backwards and forwards gives you the identity map on the second object, and that's called an isomorphism. Each of these maps is called an isomorphism, and the other one is called the inverse of the first one. And, okay. Now, just natural numbers. This is cardinal numbers. And if you have vector spaces, the category of vector spaces, with linear maps, then there's what's called a functor going from vector spaces to cardinal numbers. Okay, that's the dimension. And what does it mean that that's vector spaces with injective maps? Okay, injective linear maps. Then if you have a map, injective map between 2 vector spaces, of course, what's the functor? Abigail, if I have a vector space, then what's the cardinal number? Sorry? Yeah, the dimension, yes. So so a vector space goes to the dimension, and in D, and so well, so the first part of it being a functor is just that objects go to objects, and that's fine. But then maps have to go to maps. So there's an injective map between two vector spaces. Um, oh, I'm sorry. This is a narrow. This is not a narrow inside a category. It's it's just a the functor can be considered as a mapping, a correspondence from one. If the categories are sets, then it's just a function. So they're going from vector spaces to cardinal numbers, and so the vector space goes to the dimension. And if you have two vector spaces of V1 and V2, and the dimension of V1 and the dimension of V2, if you have an injection from V1 to V2, then you're going to get a map here, right? Elon, do you agree? Because if there's an injection, then the dimension of uh, of the range vector space, the range or codomain vector space will be greater than or equal to the dimension of the first vector space. So, but now if you have natural numbers, I won't try to extend this to cardinal numbers. Say 6 is greater than 0, okay? So 1, 2, 3. And then there's another way to make them into a category. A map between two natural numbers. Does anyone want to make a suggestion? Two non-zero natural numbers. So in the case of cardinal numbers, any two cardinal numbers have at least one arrow between them, and at most two, one in each direction. But with natural numbers, non-zero natural numbers, that means that means dividing makes sense, right? And I guess yes. Yeah, yes. 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 But which, sorry? Well, okay, but don't forget less than or equal to is not an equivalence relation. It's what's called an order relation, right? Well, they're closely related, but they're different. In fact, each one has three axioms: equivalence relation and an order relation. This is kind of fun. The first axiom is exactly the same in each case. It's called reflexivity. It's related to itself. Each element is related to itself. And then the second axiom is transitivity. That says if you go from X to Y and from Y to Z, then you go from X to Z. Yes, yes. Sorry? Yeah, I must ask people to, even though people are not wearing masks, most people are not wearing masks, I'd like to really ask people to speak up, because there's a lot of ventilation, which is again partly because of the last few years. Well, yes, but you're not saying anything.
So you suggesting that
Well, that's exactly what I had in my mind, right? Okay, and this is now we're getting into T-star algebra theory. The category of natural numbers, which is very closely related to Grimm's UHF algebra. It's very closely related to it's what's most related to is the finite dimensional UHF algebras, it's just ordinary matrix algebra. And so we've more or less agreed that if you have two matrix algebras and the order of one divides the order of the other, then one of them maps into the other, if and only if. Maps unitally, in a way preserving the unit, if and only if the orders divide, right? So that means there's going to be, just as there was a function from vector spaces to cardinal numbers, there's going to be n1 to n2 these one divides into, just as there was a function from cardinal numbers, for instance, natural numbers, into from vector spaces, for instance, finitely generated vector spaces, into cardinal numbers. There's a function from matrix algebra. Look at the category of matrix algebras with unital maps, okay? Unital homomorphism. And let's say over a fixed field, over the complex numbers. So, okay. And there's a function from here into natural numbers, okay? Because if m and maps unitally into mn prime, this implies that n divides n prime, if and only. All right. So what's the next step? Well, I've already let the cat out of the bag. Okay. So matrix natural numbers and matrix algebras. Well, I guess the next step will be supermatrix algebras, and which was what the Wim could have called the UHF algebras, and the supernatural numbers. And Dixmay did talk about generalized integers, and then that morphed into supernatural numbers. And Dixmay talked about matroid algebras. Okay, those are the ones that he's got the word matrix there. Okay, so we have like Glim UHF algebras mapping to supernatural numbers. We have to be a little careful. The matrix algebra is going to the natural number. How do we, when we define the natural number, how much of the matrix algebra are we looking at? Are we just looking at its structure as an algebra, or are we assuming that it's an MN? Okay. Well, that's the well, in fact, you can define the n in terms of the algebra. Okay. How do we do that? A number of people have been contributing to that discussion. Clarissa, do you remember? Clarissa, do you remember how you get from the algebra to the number without assuming that it's starting without assuming that it's constructed from a number. So if you just talk about mn, then it's constructed from the number n, right? But suppose you're given some algebra, and you're told it might be an mn. Then how do you tell which n it would be? Yeah, you look at the linear dimension, then you take the square root. Okay, so that's so we have a true functor for matrix algebras to natural numbers. It has this property, and but we and by the way, once we know that, then that sort of tells us that if the algebras are isomorphic as algebra, if the well, it says that if they're isomorphic, then the n is equal to the n prime. Okay, it can't be isomorphic because n is not equal to n prime because yeah. Well, we're talking about unital maps, though, right? You can map M2 into, if you want, you can map it into the upper left-hand corner, to upper left-hand 2x2 corner of 3x3 matrices. But that's getting a little more, that's moving ahead a little. We'll look at that too. But I think it's important to the UHF case from the point of view of categories is not only naive category theory, but it's barely noticeable. Okay, it's going to be very straightforward. Okay, but we had to work a bit. We had to work a bit to prove that that there was a functor from matrix algebras to natural numbers that took mn into n. Because it didn't depend on knowing the n ahead of time. Okay, well, it's the same thing here. But Grim UHF algebra, then that means by construction, by definition, it is an mn for what Dixmay wrote as an n. He took the notation m sub n, where n is a supernatural number. Okay, and then he showed that if you have the mn just as an algebra, then you can reconstruct the n. Okay, just like for matrix algebra, you're given an algebra and it might be an mn. Well, then the n is unique, and you get the function, and it's the same for Glim UHF algebras. You know every one of them comes from some n, but a priori you don't know it's unique. You don't know the n is unique. So, but if you can prove that the n is unique, then you have the functor. Okay, because it's also true. You can also show that if you have mn mapping into mn prime in a unital way, then this implies that n divides n prime, if and only n. So is it clear what it means for one supernatural number to divide another? You just take what it means for natural numbers in terms of the prime decomposition, right? This means that for each prime number, the one that divides the other one has fewer, at most that number of prime numbers in its factorization. And it's exactly that makes exactly, you can say exactly the same thing for supernatural numbers. You just look at the power of each prime number in it. As that gets larger, then you say it divides them. The smaller power divides the larger power, even if it's infinite, or even if there are infinitely many primes we're talking about, all at once. Okay, so we have to well, so actually, Glim's classification theorem amounts just to proving the existence of the functor from the category of UHF algebras with unital maps. Okay. and oh, I should say that explicitly. Okay, so and how does one conversely, if you know there is a functor, then then you if you know there is a functor from swim algebras to supernatural numbers, but take them n to n, then you have the classification. If you have the classification, you know that if the thing is an Mn, then n is unique until the functor exists. Okay. You just have to check that if n1 does divide n2, then well, that happens if and only if Mn divides n prime. It maps unitally into. Well, and at a more elementary level, we can just talk about the well, what Dijk's translation of Grimm's very rather deeper calculations was just to do some number theory, okay? And you can talk about the category of some supernatural numbers on the one hand, and on the other hand, you can talk about the subgroups of the rational numbers, okay, containing the integers. And here you would here the maps. This is a category with inclusion. It's a lot like the simple arrows over here. For cardinal numbers, you take less than or equal to, and for the natural numbers, non-zero natural numbers, you take divisibility, dividing the ratio, the relation of one dividing the other. Well, for sets, makes sense to talk about inclusion. Of course, these are additive groups, and inclusion will be thought of as a group homomorphism as well. Special group homomorphism. It preserves the energy. Okay, so this is a category. Supernatural numbers are a category. Well, in fact, these two categories are equivalent. What does equivalent mean? Well, it has a more complicated meaning, but the more down to earth, the more special meaning is the two categories are, in a strong sense, exactly the same. Okay. In fact, they're both sets. The supernatural numbers are a set, and the collection of subgroups of Q that forms a set. So we can just say they're isomorphic. There's a map between this set and this set, which and there's a map between the arrows here and the arrows here, and it's the structure being the category of the objects and the map between the arrows. Sorry, the structure being the objects and the arrows between objects. That's exactly isomorphic. It's the same thing. Okay. And this is supposed to be something that's not complete news, or not completely news. Okay, something that we're supposed to have touched on already. Does that ring a bell? Does anyone? Can anyone comment on that? So, Jared, you're saying you can't even comment on it? Huh? Oh, that's a comment. Thank you. But well, this reminds me of this is almost like but it's a kind of a legend about Alain Khan. Not maybe he's not the only one, but you ask him to explain something, he'll give you a very clear explanation. But if you would like him to explain it a bit more detail, he will give you a completely different explanation. And so you might not even recognize that it's explaining the same thing, right? Okay. So I'm afraid that's what we might be experiencing now. All right, but yes, Elon. Okay, okay, just start again from the beginning. Thank you, but well, that's the question. Okay, this is an exercise. Does there exist a map from M2 to M3? Of course, an algebra map, preserving linear, preserving product, and taking 1 into 1. Well, we're talking about 1 into 1, right? Preserving the identity. Oh. So that's a good question, because it's later, before too long, we'll look at more general maps too. Okay, and we'll have to, and the category approach will come into its own. So it's not. It could be in the present setting, it could be avoided just by saying that everything that you see is the same, more or less, right? That the supernatural numbers are the same as subgroups of Q. Does that ring a bell at all? Jared, do you remember? Now you're nodding. Okay. Do you remember some correspondence between subgroups of Q and supernatural numbers? How many? Does anyone? I see some heads nodding. Yes, Justin. Yeah. Now this some people might say that for n a supernatural number, 1 over n is nonsense. Okay, but if it's 1 over n times z, then this can be given a meaning. Justin, can you say what it is? Well, I'm sure you can say what it is. Okay, but can everyone say what the 1 over n? So, for instance, 1 over n times z. Okay, that contains z. If you look at how this is defined, where n is a supernatural number, okay, including an ordinary. If it's an ordinary natural number, non-zero, no problem, right? Okay, so the point of supernatural is that they behave almost the same. Okay, you can't. It's not adding is not so much in the works. Okay, but you can multiply them and divide just almost as well as with, essentially as well as with ordinary non-zero. Well, yeah, right. But this is the only example. That's it. Okay, and this is I'm going to keep track. How many times I have to assign this as an exercise? Right? Yeah, I mean, that's why I don't know if computers are ever going to catch on. I think paper, you have a blank sheet of paper, you've got to write something on it. So if someone says anything that looks like exercise, you write it down. Whereas if it's a computer, well, it's probably busy doing some calculation, making money for someone. Okay, so that's and the n is a supernatural number, and this is bijective correspondence. Okay, between this group, however it's defined, and the n. if the n is an arbitrary supernatural number, that means a collection of exponents, a way of associating an exponent to arbitrary prime numbers. It's a function from prime numbers to natural numbers, including 0 and also including infinity. Okay, you keep track of prime powers, and that's all you need to know. That's all you need to know about a natural number. You only need to know the exponents of all the prime factors, right? And then now addition is a little. They have to work a bit to do addition on that, but multiplication is very simple, right? That turns out to be addition on the sequences of exponents. Okay. Well, so what I'm hoping is that some people might decide to turn this into a glorious essay, the whole thing, and put it all together. But, which is, I mean, one of the things I'm hoping people will catch on to is the idea of writing an essay. And this is as good a topic as any. The good topic, a good essay topic. What is there? How much of the situation is just formulating things, and how much is proving things? How much has to be proved once you formulated things? That's I think sometimes the things are cluttered by a great deal of technical calculation work. Okay, and in that case, it's a little harder to ask people to straighten everything out themselves. Okay, but in the present setting, in the present setting, I think it's realistic to ask for an essay on the one hand, talking about the exact correspondence, which can be thought of as isomorphism of categories between supernatural numbers with arrows being division relations, and the subgroups of Q containing the number 1, which where the arrows are inclusion. And so what's an isomorphism? Jack? You're Jack. Yes. Okay. But what is an isomorphism between two objects in this category, subgroups of Q? In general, if you just say two groups, isomorphism is isomorphism, right? I mean, it's having a map between them that preserves the operation, both directions, and is bijective. That's it. That's an isomorphism between groups. You only have to say preserves the operation in one direction. That's what happens. Don't worry about that. Okay, but in this case, isomorphism of two of these objects, they're special groups, right? They're subgroups of Q on the one hand, and they're assumed to contain Z. And and furthermore, okay, I guess I should have said that all the isomorphisms are inclusions, right? Well, actually, you don't. If it's any bunch of subsets of a set, and you consider them as a category where the maps are inclusions, the arrows are inclusions, then you can say what an isomorphism is, right? It says the first object is contained in the second, and the second object is contained in the first. This is set theoretic conclusion, right? So what's the upshot of that? Well, I guess if two sets are going, if they're ever going to be equal, then they're equal, and that's true, right? Each one is a subset of the other. So that's what an isomorphism is. In this category, isomorphism is just equality. And furthermore, that's what it is here. If you have two supernatural numbers, and each one divides the other, and in fact, that's what it is for the cardinal numbers too. If each one, in a sort of a relationship, if you look at the exponents, then it's the cardinal numbers of the exponents you're looking at. But anyway, if you have two supernatural numbers, if there's an arrow in both directions between two supernatural numbers, then there's an arrow going forwards and backwards, and only one arrow from something into itself, namely the identity. So anyway, what's the upshot of it for the two supernatural numbers? If even if there's an arrow going in both directions, forget about being an isomorphism. Carissa? It's the two supernatural numbers, n and n prime. And you have a map in one direction and then a map in the other direction. So what does that say? Yeah, because this one says that the first one says one divides the other, and the second one says the other divides the first. And in terms of the exponent, just that. Well, in general, there are, and between groups there are non-trivial isomorphisms. But in this case, and even when you can see how interesting to me. But point is that that's injecting an illusion by talking about isomorphism of sets as opposed to equality of sets. Okay, these 1 over n from z. When you look at the mn tensor k,
you can get that group, but you can't get it in a way that contains Z. You get it up to isomorphism. You get the group K0, okay? K0 is a functor. You look at this algebra, you take the K0 group, which is isomorphic to a subgroup of rational. It's isomorphic to this. If you're looking at Mn tensor K, then the K0 group is isomorphic to this, but not in any canonical way, because you don't have the class of the unit. You don't know what the unit was. So you're just giving you. So the non-trivial, the reason for talking about the category theory in the trivial case, where everything is equal, is that in the called the stabilized case, Mn tensor K, what's important, you have them n and n prime. You look at the two groups, 1 over n times z, 1 over n prime times z. Then the algebras are isomorphic. Well, if they're isomorphic, then well, it's if and only if the groups are not equal. The equals make sense, okay, but they're not don't have to be equal. They just have to be isomorphic. So Jack, you've put your finger on a sensitive place, okay, and I'll have to repeat it next time, but for benefit of people online or maybe for the benefit of for everyone, including me. Well, any questions, then we can meet in the front of the room or outside. And I highly recommend the Friday afternoon office hours of Mr. Ball.